morning. This is a model 4 discrete time Markov chain, lecture 6 time reversible Markov chain, and then application of irreducible Markov chain in queuing models. So, in this lecture I am planning to give the time reversible Markov chain and how to compute the stationary distribution in a easy way. Then I am going to give applications of irreducible Markov chain in queuing models. Here irreducible Markov chain means it is a DTMC model, because later we are going to give the applications of irreducible continuous time Markov chain in queuing models also in the later lectures. And also I am going to give few simple examples. What is the meaning of a time reversible Markov chain? First, let me explain how to construct the time reversible Markov chain. Consider a DTMC, it is of course a time homogeneous discrete time Markov chain. You see the collection, it is in the usual way xn minus 2, xn minus 1, xn plus 1, xn plus 2 and so on. Now, you trace the DTMC backwards. That means you know the first all xn plus 2, then xn plus 1, then you know what is xn, then you collect xn minus 1, xn minus 2 and so on. Now, the question is whether if you make a DTMC backwards and that sequence of random variable, that is of course, it is a stochastic process, whether this is going to be a DTMC. Any stochastic process is going to be a DTMC if it satisfies the Markov property and the state space is discrete and the time space is also discrete. But if you see this the DTMC backward, that is also going to satisfy the Markov property. The way the given situation, the future depends only on the present, not the past history, that is a Markov property. The same thing is going to be satisfied in the reverse also. The Markov property is satisfied by the reverse, the backward DTMC. Therefore, this is also going to be a time homogeneous discrete time Markov chain. Now, I am going to define what I am going to give, how to find out the one step transition probability for the reversible process, that you take it as the matrix Q that consists of elements Q I J. You can find out the entries, the Q I J, that is nothing but what is the probability that the system will be in the state J at the nth step, given that it was in the state I at the n plus 1th step. That is different from the original DTMC. The original DTMC, it is what is the probability that the system will be in the x n plus 1 in the state J, given that x n was I, whereas here it is x n is equal to J, given that x n plus 1 is equal to I. This conditional probability you can compute in this way: the product of probability of x n is equal to J multiplied by the probability of x n plus 1 is equal to I, given that x n is equal to J, divided by what is the probability that x n plus 1 is equal to I. That is same as the probability of x n is equal to J is nothing but in a steady state, what is the probability that at the nth stage in the system will be in the state, that is equal to pi j multiplied by what is the probability that this is the one step transition probability of system is moving from J to I, divided by pi I. That means the Q I J is going to be pi j P j I divided by pi I, assuming that the stationary distribution exists. Otherwise, pi j is equal to limit n tends to infinity of P I j n. Now, I am going to give the definition of a time reversible. A DTMC is said to be a time reversible DTMC if both the transition probabilities are one and the same. That means the one step transition probability of the new or the time reversible process Qij is same as what is the one step transition probability of the original DTMC, that is Pij. That is, the reverse DTMC has the same transition probability matrix as the original DTMC. Now, I am going to equate this, the Qij is equal to this much. Therefore, that is same as pi j of Pji is equal to pi I of Pij. And if this equation is going to be satisfied, then that DTMC is going to be called it as a time reversible Markov chain. And this collection of equation for all Pij, that equation is called a time reversibility equations. Now, I am going to give the few results on time reversible Markov chain. Let me take a irreducible DTMC. If there exists a probability solution, that is pi is the vector, satisfies the time reversibility equations, that is the vector pi consists of pi 1, pi 2 and so on. So, if that entries satisfies the time reversibility equations, that is pi I is equal to pi I times Pij is equal to pi j Pji for all pairs of I comma j, then the DTMC has a positive recurrent states and also it is a time reversible, and the solution pi is a unique stationary distribution. That means whenever you have a irreducible DTMC and if you have there exists a probability solution vector pi satisfies the time reversibility equation, then we can conclude that DTMC has a positive recurrent states as well as that DTMC is a time reversible Markov chain. Also the vector pi that satisfies the time reversibility equations, that vector pi is a unique stationary distribution. So, the how one can use the time reversible concept in finding the stationary distribution, that I am going to explain in the next example. Let me take a simple example which consists of 4 states. It is a finite model, finite state space. Also it is irreducible because each state is communicating with each other states, and I assume that the probability p that is lies between 0 to 1. Therefore, this is going to be a periodic states. So, this Markov chain is a finite, irreducible, and you have the result for a finite irreducible Markov chain, at least one state is going to be a positive recurrent. So, since it is irreducible, all the states are of the same type, therefore, all the states are going to be a positive recurrent states, and also it is a periodic. So, you can use the result of a irreducible, a periodic, a positive recurrent and also the finite states going to give the unique stationary distribution, and that can be computed by solving pi p is equal to pi, where pi is the stationary probability vector. Here you can use the time reversibility concept. Therefore, you do not want to solve actually pi p is equal to pi, but you can start from the time reversible equation. From that you can get the solution. That is what I have done it in this example. First I have checked it is irreducible, then I check whether the time reversible equation is going to be satisfied by this irreducible Markov chain. So, since it has the 4 states, I am just checking all the states whether the time reversibility equations are going to be satisfied. That is satisfies. Since it is, you see the previous result for a irreducible DTMC, if there exists a probability solution, that means I started with there exists a solution, but since I know the result, it is a irreducible, aperiodic, positive recurrent, and the stationary distribution exists. Therefore, I started with the probability solution pi, and I have checked it the time reversibility equations for the example also. Then I am concluding it is going to have a unique solution. So, I have checked. I have verified whether I have verified the time reversibility equations. After the time reversibility equations, from that I am getting the pi n in terms of pi naught, because the way the recursive relation goes, you can make out pi 1 from the first equation, you can get pi 1 in terms of pi naught. Then the second equation pi 2 you can get it in terms of pi 1, then in turn you can get pi 2 in terms of pi naught. Similarly, you can get pi 3 in terms of pi naught. Now, you have to find out what is pi naught. Pi naught, you can use the normalization equation, that is a summation of pi a is equal to 1, that is pi naught plus pi 1 plus pi 2 plus pi 3, that is equal to 1. From that you can get pi naught is equal to 1 divided by 1 plus p divided by 1 minus p square by 1 minus p whole square plus p cube by 1 minus p whole power 3. So, this is going to be the pi naught. Substitute pi naught in this pi n, therefore, you get the pi n also. So, we are getting the unique stationary distribution, because this DTMC is a time reversible. Therefore, without solving the pi p is equal to pi, you are using the time reversibility equation itself, and summation of a pi a is equal to 1, you are getting the pi a's. So, that is a easy way whenever the DTMC is going to be a time reversible Markov chain. So, in this example, we have used the time reversibility property to get the unique stationary distributions. In the result, we said there is a, and the solution pi is a unique stationary distribution. So, in the results needs only the proof whether the pi is going to satisfy the equation pi p is equal to pi. So, that can be easily proved by taking summation of pi i's p I j, that is same as summation over I pi j of p j I, because it satisfies the time reversibility equation. We can write a summation over I pi I times p I j same as a summation pi j p j comma I. That is same as, you can take out the pi j outside, that is same as the summation over I the p j I, and you know that the summation over I the p j I, that is going to be 1, therefore, this is going to be a pi j. So, hence we get summation over I the pi I of p I j, that is equal to pi j. So, this is nothing but in the matrix form pi p is equal to pi. So, whenever you have a irreducible DTMC and satisfies the time reversibility equations, then you have a unique solution pi, and that pi unique solution is a stationary distribution. So, and also you can prove easily it has the positive recurrent state and the time reversible Markov chain also. So, with this proof, we have got the result that the pi is going to be a unique stationary distribution, and also I have given the example how to use the time reversibility equations to get the unique stationary distribution.